you recollect, we were talking about Huffman coding procedure, which is almost an instantaneous source coding procedure for discrete sources, and this is a summary of the procedure that we discussed yesterday. We are just displaying the whole thing again for your information. Do you have any question regarding this procedure? Is understood? I think it's a very simple procedure.
Sir, one question is there. If there are only two messages M1, M2 and probabilities are not equal,
we'll take care of that case in a few minutes. But the basic procedure is you have a dictionary of message symbols in the source, each having some a priori probability of occurrence. You arrange these messages or symbols in the order of decreasing probability, and then keep on creating new sources of smaller sizes, smaller dictionaries, by clubbing the two lowest of these message sequences or message symbols in this list, and eventually you are left with only two messages with very nearly equal probabilities. At that stage you start doing a bit mapping, and rather arbitrarily at this stage, and then keep on tracing back for distinguishing between those sources which were those equivalent sources which were the result of clubbing two other sources, or two, not sources, I should use the word messages or symbols, right? And this procedure is quite efficient as seen from this example. As I said, one could verify that the entropy of this source is 2.45 bits per symbol, whereas the entropy is 2.418 bits per symbol, whereas the average length of this code that one has finally come up with is 2.45 bits per symbol, right? Because some messages have length 2, are represented by 2 bits, and some are represented by 3 bits, and if you take the average depending on the probabilities, using the probabilities, the average value turns out to be 2.45 bits per symbol. And one can define a quantity which is a measure of how good your coding procedure is, and it's called that's right, it's called code efficiency. Usually denoted by the symbol eta, and as I said last time also, it's a ratio of the entropy of the source to the average length of the code that you have finally got. And for this particular case, this will be 2.418 upon 2.45, which is of the order of 0.97 or so, right? That is 97.6% efficiency. Obviously the maximum value of efficiency is unity, or 100%. We also define a complementary quantity which is called the redundancy of the code. That is, the transmitted signal or transmitted message is still having some extraneous information, some extraneous value, and that is basically defined as 1 minus eta, which in this case will be 0.024. Okay. So Huffman coding is a good coding procedure, and there are other such coding procedures available which can do nearly as well, but it's one of the more popular procedures because of its simplicity. Now there will be situations like the one that was just pointed out by Varun, where it may not be sufficiently good to carry out this coding on a single symbol basis. The Huffman coding procedure carries out this coding on a single symbol basis. That is, as each symbol is emitted, you immediately associate a corresponding code for it. For example, if M1 is emitted by the source, it will be represented by the string 00. If M4 is emitted, it will be represented instantaneously by the string 011. And this is unlike the source coding argument that we discussed yesterday earlier on, in which one had to wait for an infinite sequence of emissions before one started the coding procedure, right? So that was one extreme where the coding delay was infinite. This is another extreme where the coding delay is 0, no coding delay, right? Because you have a code immediately available to you. As each symbol is emitted, you can just carry out that mapping and you have the encoded value. Now, it's sometimes not good enough to do this kind of a thing, that is instantaneous coding. In this particular case, it turned out to be good enough, right? In which case, it may be worthwhile to do a compromise of the two, right? One need not wait for infinitely long message emissions. One could take 1 or 2 or 3 message emissions rather than only one, and then code this together, right? And one could get considerable advantage by introducing that small amount of coding delay and achieve a code efficiency of nearly unity, right? Even if it was difficult to do so on a single symbol basis. To demonstrate this, incidentally, this kind of coding, Huffman coding, one can have Huffman coding procedure based on a bit of coding delay of this kind. These are called higher order Huffman coding procedures. Okay. For example, I could have a second order Huffman coding or a third order Huffman coding. Usually one doesn't go beyond a few values like this, 1, 2 or 3. One doesn't in any case go up to very large values like one has to do for the ideal case that we discussed. Okay. Let me illustrate what advantage we can get out of going for higher order Huffman coding by taking a very simple example where our message source is comprised of a very simple kind with only 2 outputs, M1 and M2, right? And if they are equiparable, then we don't have to go through Huffman coding, right? For example, if each of them M1 as well as M2 is emitted with equal probability of 0.5 each, the obvious thing to do is to allocate 0 and 1 arbitrarily to them, and that's the best one can do because it's the entropy of the source is 1 bit per symbol, and that also will require 1 bit, and therefore you have a code efficiency of unity. One doesn't have to do anything beyond that. Is it clear? On the other hand, let's take a situation where the probabilities associated with the 2 symbols are very unbalanced. Let us say 0.8 and 0.2 respectively. So 0.8 is the probability of emission of M sub 1 and 0.2 is the corresponding probability for M sub 2. Okay? And it is very easy to check that the entropy now is not 1 bit per symbol as it would have been if both had equal probability of 0.5 each, right? But it is obviously less than 1 because equal probability case gives you the largest maximum entropy. It turns out to be 0.72 bits per symbol. You just carry out the computation and verify that. And now if you do a straightforward allocation of 0 and 1 to M1 and M2, what is your code efficiency? 0.72, right? Because your code length is 1 bit, but the average information being conveyed by this code per transmission is only 0.72 bits because that's the entropy of the source. Alright? So efficiency is only 0.72 or 72%. Now this is where it will be worthwhile investigating or going for a higher order Huffman coding procedure, right? And the higher order Huffman coding procedure now lets a few bits, a few message outcomes accumulate before you think of coding. For example, let's consider the second order case. All right. Now, that is, we'll take n equal to 2. We now think of a new message source whose outcomes are two successive outcomes of this source, right? And obviously there are 4 possible outcomes with different probabilities. These are M1 M1, M1 M2, M2 M1, M2 M2. All right. First could be M1, second could be M1, like that, and so on. And if we assume that successive emissions are independent of each other, then we can compute the probabilities of each of these 4 message values that we have now, 4 message symbols. You can think of these as a new source with 4 symbols as its output, as its dictionary. Okay, and the corresponding probabilities are, what will be the probabilities of this sequence? 0.64, 0.16, 0.16 and 0.04. Right, and of course I have written them out again in the order of their decreasing probability, and one goes through the rest of the procedure in the same way. Should I do it? All right, although I don't think it was necessary, but since it is a very small one, we can do that. The next one will be, we will club these two to get 0.20, and this is 0.16. This one comes here. These two are clubbed together again. Now you get all right. Now we still haven't got them really equal, or very close to equal, but they are better than what we started with here, 0.8 and 0.2. Right, the discrepancy is less here. If you go for a third order situation, you will find that the eventual discrepancy is even lower. Right, that's the advantage of waiting for some time in some cases. So one can start with a bit allocation of some kind. For example, I could do a 0 here and a 1 here. All right, and this will, at this stage it will become 0. This will become 1 0 and 1 1. This will be 0, and this 0.16 will be 1 1. Right, this 0.16 will become 1 0 0. Right, and this will become 1 0 1. So this will be your final code. M1 will be represented by 0, this by 1 1, and so on. Okay, so you will wait for 2 successive message emissions and then carry out the coding. So it won't be now instantaneous coding, it will be coding with unit delay. Right, and one can check that the average length of this code, if you were to just go by these probabilities, 0.64 into 1, plus 0.16 into 2, plus 0.16 into 3, plus 0.04 into 3, that will turn out to be 1.56 bits per symbol of this source. But this source is conveying how many symbols actually of the original source? 2 symbols. Right, so of the original, let me call this L prime. So average length L with respect to the original source is 0.78. And now what is your code efficiency? It's 0.72 upon 0.78, right, which turns out to be about 0.92 or so. So is it true? The entropy was 0.72 and the average length is very close to that now. It's 0.78. Right? So our efficiency has gone above 90%. One can check that if you take n equal to 3, you will get 98 or 99% efficiency, which is very good. So sometimes it's worthwhile introducing a bit of coding delay to get better efficiency, representation efficiency. Remove as much of redundancy as possible in the source emissions. Is it okay? Please speak out if you have any doubts left. Okay. No commission. Nikhil, is it okay? Fine. So that is as far as what I wanted to cover of source coding. This is a very brief glimpse into what source coding is all about. It's a fairly vast subject on its own, and there are various kinds of sources and various kinds of source coding procedures to take care of those sources. But in the short time that we have available with us, I only wanted to give you an idea of what source coding is all about and what we can achieve by doing source coding. Okay? But the basic purpose you should not forget. The basic purpose is to come up with an efficient digital representation of your source outputs. Okay? So that we don't burden the channel unnecessarily by transmitting redundant information. Basically, that's the idea of source coding, right? Because channel time is important and expensive, because it's composed of a lot of infrastructure and a lot of equipment which costs money. So we have to efficiently use it. To efficiently use it, you must make sure that we avoid sending redundant information unless we are doing it deliberately for some other reason, right? But per se, we will not like redundancy to be transmitted, because it means waste of channel capacity. Okay. Now, with this background about source coding, I'll now like to briefly motivate you about Shannon's result regarding error-free communication, the possibility of error-free communication over a noisy channel. This is what we talked about when we started discussing information theory. Do you recollect that discussion? See, what we have learnt till now in information theory is that if you have a source with entropy HM, we can transmit by appropriate source coding procedures, we can encode it into a digital representation which require on an average HM bits per message symbol, right? One can carry out an encoding procedure, and if your coding procedure is good, we can hope to achieve this kind of representation of the message, and we could of course simply transmit this on the channel. If you do that, we call this zero redundancy coding. Now, this can be very risky also. While it is good from the representation point of view, from not burdening the channel unnecessarily with redundant information point of view, but it can be a very risky thing to do in real life. Why? Because real life channel is going to be noisy. Now, anything that you transmit now, something that goes wrong because of noise, there is no way to know whether what you have received is what was transmitted or the result of distortion or degradation due to noise, because there was absolutely no redundancy, right? You expect whatever you receive to be hard information, right? Whether it is ones and zeros, you will accept it at its face value because it was supposed to be the true representation of the source, right? Now, whether it is really the true value of the source that you are receiving, or whether it's a result of that having undergone some changes because of an error probability in your receiver, right? There is no means to know, right? So there is therefore this problem that if you carry out zero redundancy coding, the noisy channel is going to create problems for you. That means it is not possible in such a situation to have error-free communication. If you stick to zero redundancy coding, and it follows therefore, it's more or less obvious that use of or introduction of certain amount of redundancy is going to help us to combat these noise problems. For example, you are all familiar with the use of parity check codes, right, in various kinds of systems, including communication systems. Okay, suppose you are using that kind of parity check coding, and suppose you are doing this parity check coding on a source with entropy HM. Typically, what you are doing is to every bit, to every word of the source output, you are adding one extra bit, right? And your code efficiency therefore becomes all right.
This is for what?
This is for parity check coding. You just add one parity check bit, right? That's what a parity check coding is all about. Add one additional bit to every word, or every message word that you have. Okay, if average, if length of the message is HM bits, you're adding one extra bit, making it HM plus 1 bits, right? That 1 bit is not really the original information. It has been deliberately added by you as a redundant bit, right? It's not really conveying any new information, but we know that at the cost of going from 100% efficiency to less than 100% efficiency, the advantage that you will get is an ability to be able to say when errors occur, be able to at least detect that errors have occurred. Some kind of errors have occurred, right? Which ability was totally missing in the original situation, right? Is it clear? So, as eta decreases, or redundancy, what will be redundancy in this case? 1 minus this, which will become 1 by HM plus 1. So, from 0 redundancy, we have got a finite value of redundancy. As gamma increases, we get some means to combat noise. We already know about parity check code, so therefore I took this as an example. In general, the moral is that one can increase the immunity against channel noise by introducing certain amount of redundancy in your transmission, right? Immunity against channel noise can be increased via introduction of redundancy. Okay, and it is this which brings in the possibility of achieving error-free communication over a noisy channel. Let's discuss how.
So the noise would be that in the message signal the bits are, let's say, flipped. And instead of the message signal bit being flipped, suppose the parity bit is flipped. The message signal is transmitted okay.
I'm not discussing the mechanism of this coding and decoding, right? Actually, just to answer your question very briefly, an appropriate code will be able to detect where the error has occurred, independent of whether it is in the message bits or in the parity bits. Okay, but we are not going to that at the moment. Okay, a good, well-designed code will be able to make, will be able to find out where the errors have occurred and what those values are, right? Provided it's a proper error correcting code. But if it is only a parity check code, there is only so much you can do with it. You can't do very much. You can only detect errors. In fact, you can't even find out where the errors occurred. You can only detect the occurrence of an error, right? Nothing more than that. But anyway, we are not discussing that at the moment. We are only discussing what we can do, what we can eventually hope to achieve by doing this kind of coding procedure, right? And I want to, actually speaking, introduce the concept of channel capacity to you, which is a fairly slightly abstract concept which I want you to understand. Let's take the example of what we sometimes call a binary symmetric channel. Before going to that, please remember what is it that I have said which I want to further discuss. What I have said is that I can get some kind of immunity against channel noise by introducing redundancy. The question is how much redundancy one has to introduce. Okay, that question is I am going to illustrate slightly by taking an example of what is called a binary symmetric channel. Okay, now a channel, a physical channel that we have been discussing in the first course in communication as well as this course is one which is comprised of the transmitter, the physical medium, and the receiver. I think there is some disturbance. Can you shut the door? Is the door open? Okay, then it's fine. Let's return to this binary symmetric channel. This is a model that is used for representing physical channels in a binary situation, in a binary signal transmission situation. Okay, where see you may have a specific digital modulation scheme, you may have some physical channel with a certain kind of noise, let's say Gaussian noise, and then you finally have at the receiver the match filter followed by sampler followed by your decision device. But if you look at this, if you regard this whole system as a black box, what is the input to this? It's a sequence of zeros and ones, right? It's a digital system, digital communication system. The input is, let's say, a sequence of zeros and ones if you are assuming binary sources as the input, right? Similarly, the output, the final output, the very final output is again a sequence of zeros and ones, right? So every 0 or 1 that is transmitted here is received as hopefully a corresponding 0 and 1 here, except when errors occur, in which case a 0 may be flipped as 1 and a 1 may be flipped as a 0, right? So when you model the channel or the communication system as a black box, in this sense, looking at only the absolute inputs, the very first input that you are giving in terms of binary values and the final outputs in terms of binary values, that resulting model is described by various kinds of models, and one of the models is what is called a binary symmetric model for this kind of channel. And what it says is, okay, in the binary symmetric channel, the model is that a 0 will be received as a 0. Let me draw it separately. Usually it is represented like this. A 0 will be received as a 0 with a certain probability p, and will be received as a 1 with a probability 1 minus p. And if it is a symmetric model, the same will be true for 1. A 1 will be received as a 1 with a probability p and as a 0 with probability 1 minus p. Obviously 1 minus p is then equivalent to the error probability calculations that we have done so far, right, for various systems. So the value of p and 1 minus p will depend on what specific system configuration we have, how much noise we have in the system, how much bandwidth we are using, and all those things. The exact design of the system will dictate the value of p, but a single parameter finally is sufficient to describe the overall performance of the channel, or performance of the system in terms of inputs and outputs, and that parameter is p. Of course, calculation of this parameter further requires you to go deeper into the communication system and understand how to calculate it, like we have done for various situations. Okay. Now, for this kind of a channel, which is described by this parameter p, or let me describe it by a parameter p sub e, which is the error probability associated with it, right? It can be shown that we have a channel capacity C sub s, which is given by this formula. sorry, log okay. If we have time, we will even prove this formula later, but at the moment I just want to introduce a concept. This CS is a number which it's very easy to verify from this expression that it will be less than 1, and that's precisely what can be calculated to be the channel capacity of the binary symmetric model associated with the binary symmetric model. Log to the base 2. Okay. That's precisely what we are discussing. Okay. Now, remember at what point I digressed into this. The point was I wanted to discuss that immunity against channel noise can be increased by introducing redundancy, and the question I am addressing now is how much redundancy one has to introduce, and the answer is that depends on the channel capacity, right? This number channel capacity associated with a specific channel model. For example, if you have a channel capacity, let's say 0.4, okay, then you will require an average code length equal to 2.5 times HM, because the result is that if you have a source with entropy HM and a channel of capacity C sub S, then you must use on an average so many redundant bits. An average code length of this value, HM divided by C sub S. That is how this 2.5 HM comes up. Okay, this tells me that for every bit of the message, for every bit of the message symbols that I transmit in this particular example, I must transmit 1.5 redundant bits. Right. So this notion of channel capacity tells me how many redundant bits I must add to my basic information which I am interested in sending. What I am interested in sending is an average information rate of HM bits per symbol, right? But if I want some kind of immunity against channel, then that tells me that I must add up at least 1.5 bits to every single bit of the message symbol that I transmit, so as to hopefully get some kind of immunity, reasonable immunity, or possibility of error-free communication on a channel of this capacity. If the capacity was 0.8, then obviously it will come down. The amount of redundancy that we need to add becomes, the need for having additional redundancy also correspondingly comes down. So if CS is 1, you have a perfect channel, right? No redundancy is needed, and obviously that will be hopefully a situation with what kind of situation? P equal to 0, that is no noise is present in the system, right? So somehow we have the amount of redundancy that we end up using will require to use depends on this notion of channel capacity. This is just through an example I wanted to illustrate what channel capacity eventually will tell us. How does it come into the picture is something that I take up now, right? But suppose I eventually I am able to understand what channel capacity is. This is how it. This is the kind of thing I can do with it in system design. Okay, this kind of conclusion I can draw from this. Now, the importance of what Shannon said was the following. I am just trying to recollect for you now what we discussed on the very first day when I started discussing information theory. Do you remember we discussed the trade-off between error probability and signal power and data rate, right? Our conventional classical communication theory that we have read so far tells us that if I want zero error probability or error-free communication, either I must increase my average transmission power to very large values, infinite values, or I must decrease my data rate or information rate down to 0, isn't it? So as to make the average power, average energy per symbol very, very large, infinite, and therefore eventually get the same zero error probability situation, right? Now this is where Shannon came and changed things. He said that it is not necessary that your average information rate be brought down to 0. Okay? It is possible to get error-free communication even when the average information rate is finite and your transmitted power is also finite. The only thing you have to make sure is that the average information rate that you transmit is no more than the channel capacity. A number, a constant number, which we call the channel capacity, which is a function of the transmitted power as well as the, let us say, the noise that you have in the channel, the total noise that you are dealing with in the channel. So importance of Shannon result is precisely that it is not really necessary to let the transmission rate or the information rate for error-free communication to be made 0. What is really necessary is that suppose I denote this transmission rate by, say, f sub naught, right? It's only necessary that f naught be kept below a constant value c, and that constant value is your channel capacity measured in bits per second. These are the units of channel capacity. Okay. Now, if you combine these two information, here I said CS, this number CS I define to be a number less than 1, right? What does this represent? That for every symbol that I transmit, every symbol that I have to transmit, I have to the number of effective bits that I can transmit per symbol is essentially 0.4. That's what it means, because the 0.6 part of it has to be redundant bits. That's the meaning of that, right? See, when I said that I need to add so many redundant bits, my total number of bits have to be so many, right? In other words, one can imply it to mean that for finally, what if you transmit 1 bit, out of that 0.4 can be your information and 0.6 has to be the redundant part. For example, here we discussed if you transmit 2.5, then 1 is your information bit and 1.5 are redundant bits. Now, if you take the fractions, right, this is what it means. If you're transmitting a single bit, out of that single bit, the information being carried by that bit is only 0.4 bits, right? The rest of it is redundant information. That's another way of looking at this capacity of the channel, this measure of capacity of the channel, which is dimensionally less than 1, which is dimensionally a constant and less than 1. But if I want to convert into bits per second, how will I do that? That will depend on how many symbols per second I can transmit on that channel, right? Which I already know from my other theories. From, for example, my Nyquist theory, that tells me how many symbols per second I can transmit on a particular channel. For example, if your channel has a bandwidth B and it's a band limited channel, I know that I can hope to transmit symbols without inter-symbol interference at a maximum rate of 2B per second, right? And therefore, I can combine these two results and say that this will be equal to 2B times CS. Okay. If I transmit 2B symbols per second and every symbol is allowed to carry only this much information, that's what channel capacity really means. It tells me what is the maximum amount of information that every single symbol that you transmit on the channel is allowed to have. Right? Then this is a measure of my overall channel capacity. It's a slightly abstract notion, but if you just think about it, it's very easy to understand what we are talking about.
So that means at the source, when you are after coding and all that,
Yes.
the symbol rate will be 2B CS or only CS? Symbol rate will be 2B.
No. Channel capacity is absolutely independent of source. It has nothing to do with source. It's an attribute only of the channel, just like the entropy was an attribute only of the source. It told me how much average information is coming out of that source. Right? Similarly, channel capacity is an attribute purely of the channel. It tells me for that kind of a channel which has this kind of noise and on which this much power is being transmitted, what kind of redundancy must be introduced. That is, if you are transmitting a symbol, what should be its composition in terms of information part and redundant part. Every symbol that is transmitted, for example in this case, must not carry more than 0.4 bits of information part, and the rest should be redundant information. So it's an attribute only of the channel. It has nothing to do with the source. Please try to understand this. One, entropy is an attribute only of the source. Two, the channel capacity is an attribute only of the channel. That's why it's called channel capacity. Okay?
But here we define CS in terms of probability of
Probability. That is
CS in terms of?
probability of error.
That's right. It depends on, I said, the kind of noise you have in the system. It depends on the kind of signal power that you're transmitting. And for the binary symmetric model, all that is embedded in your error probability.
That is also depends on single power.
That's right. Error probability depends on signal power, noise power, everything.
This channel capacity will also depend on single power.
Obviously, it will depend on everything that you have in the communication system. Only thing is, for the binary symmetric channel, the only parameter that you need to finally calculate this number is this error probability. You must somehow calculate that number first, and then you are able to calculate your channel capacity. So it's an indirect way of doing things. Have you understood the concept?
at this rate we can make sure that no error will be occurring.
Now we are coming to that. This is what Shannon said. Shannon said that if you make sure that your data rate is less than, your information rate is less than this number, this constant number, which is this, right, which will depend on the channel, kind of channel you have, then it is theoretically possible to expect error-free transmission by some means or another. Okay, that's what Shannon said, and I like to try to justify how this kind of an argument can be given. This is quite against our normal expectation, isn't it? Because normal expectation is no matter what you do, if you want zero error probability or error-free communication, you have to either have infinite signal power or you have zero error rate, zero data rate or information rate. Okay.
Is it given we have an exact model of this channel?
Can you repeat your question,
Is this
please?
for a given model of channel?
No, this result is independent of what the value of the channel capacity is. The value of the channel capacity will depend on the specific channel, right? But this result is absolutely general, right? This number will be different for different channels. The capacity of the channel will depend on what channel you are working with, what kind of modulation scheme you have, what is the physical path, what its bandwidth, right? All those things will determine what C is. But once you have that value C, then this is the result to use. Yes.
The maximum rate we are in the channel of bandwidth B is 2B, right? And
Symbol rate,
symbol rate.
right?
And if we define because CS is nothing but the efficiency. So out of the
CS is not efficiency.
effectively turns out to be
Okay,
that.
you can put it that way.
So
Yes.
effectively out of 2B bits, the number of the information bits are are 2BCS.
2B symbols. Please distinguish between symbols and bits.
Fine.
Right?
It is 2B into CS.
Right.
And the remaining is redundant information.
That's right.
So that's how you.
That's right. So the one of the answers he has already given, that this result is coming because we have redundancy, right? Because everything that we are now transmitting is not pure information. Along with information, we have agreed to waste our transmission capacity to transmit also redundancy, right? But the question is, how does redundancy also create this kind of a situation? That is what we need to understand, right? And that's what we like to understand next. How we can get from introduction of redundancy the possibility of error-free communication. This is what we'd like to understand next. So let's look at that. It's clear that if at all this result has come from somewhere, it has come from redundancy, transmission of redundancy, redundant information, isn't it? Because this is the only additional thing we are doing which we are not thinking of doing earlier, right? So somehow transmission of redundant information has a major role to play in getting Shannon's result. So let us see how redundancy can lead to this kind of a result. Mind you, my argument is going to be purely intuitive. This is a result which Shannon proved mathematically very rigorously, but we have no time and scope for doing that mathematical argument, right? We will only discuss intuitively how this result can be justified, right? We will only look into a justification for this result, nothing more than that. And that justification will be easy to understand if you understand the role of redundancy in error-free communication. And to do that, I'll take a very simple kind of simple method of introducing redundancy. Suppose I have a very simple kind of a source in which outputs are zeros and ones, right? And I introduce redundancy in the following way. Every zero that comes along, so it's 1 bit of output that is coming out. I add two redundant bits, both equal to whatever has come out. Right? For example, if 0 comes out, I transmit not 1 bit, but 1 0, but transmit 3 successive zeros. Right? Similarly, if 1 is emitted by the source, I transmit 3 successive ones. This is called redundancy by just repeating. Okay, you just keep on repeating a few times, maybe 3 times, maybe 5 times, whatever bit or symbol has been emitted by the source. Very simple way of introducing redundancy. Now, if I do that, you can already see something, that at the receiver, what you will receive is not necessarily 0 0 0 or 1 1 1, right? Something may change because of noise. You may make a wrong decision because of noise, because of your finite error probability. Maybe 0 0 0 will become 0 0 1 or 0 1 0 or 1 0 0, right? It can also become 0 1 1, but the probability of that occurrence is going to be smaller than one of the bits only going in error, right? So therefore, at the receiver, I'll now also have a decoder corresponding to this encoding scheme, which in this simple case we can predict what it should be. It should be a majority logic, right? The decoder should be essentially a majority logic system, which will decide the correct symbol based on the number of major symbols that you get here. So if you get 2 zeros out of 3, you'll say a 0 was transmitted. If you get 2 ones out of 3, you'll say a 1 has been transmitted, right? So there is already you can see the possibility of reducing your error probability as far as this 0 and 1 is concerned, right? And so I can correct how many errors? Up to 1 error can be corrected by this simple repeated transmission scheme, right? If there are more than 1 errors, there is no way to, you will make a wrong decision, right? But since we are working on the assumption that more than 1 error will have much smaller possibility of occurrence, right? Of course, this doesn't lead you to Shannon's result straight away. Okay.
See, it's also really valid. Then actual transmission, suppose you have an error.
Yeah.
It might be because some disturbance is in the surrounding of the channel.
Whatever may be the reason.
Some spike in a nearby channel which might cause some disturbance there. So the chances of getting two errors simultaneously, is that really that low?
Well, if it is a well-designed system, yes. Yes. If you have a problem in which you have to worry about man-made disturbances, then your communication channel model has to be not different. It has to be different from additive wide Gaussian noise channel model. At the moment, we are discussing additive wide Gaussian channel noise model. But if
Shannon's result is true in all cases, or for only for
this result was derived only for additive wide Gaussian noise channel, right? Which is the most common model that one has to worry about for most kinds of channels. But yes, there are situations where your kind of noise disturbances are there. Then the results are different, but corresponding results exist also for those cases. Okay. We must understand the limitations under which we have this result. Okay. So the moral is that we can increase these repetitions and our capacity to correct errors will also improve. For example, if instead of doing a repeated transmission of only 3 times, I do a repeated transmission 5 times, how many errors can I correct? 2 errors, right? I can correct 2 errors, and so on. By introducing more redundancy, I can correct more number of errors, and that is what we can understand from this. Now, let me try to put the same thing, try to understand the same thing through a geometrical picture, and that picture is going to be very crucial for us. Let me draw this picture here. Let me consider the same code in which a 0 is represented by 3 zeros and a 1 is represented by 3 ones. Now, how many different possible sequences I can receive at the receiver? 8 possible different sequences, right, corresponding to 3 received bits that I have. I can represent these 8 bits as 8 vertices of this cube, right. Let's say the origin is the sequence 0 0 0, and I'll number the vertices carefully. Let's say each axis here, I have 3 axes, x, y and z. I can only change 1 bit along each axis. Let's say this bit will be affected. I think this can be 0 1 0, this could be 0 0 1, and this could be 1 0 0, right. So this bit is affected along this axis, this bit is affected along this axis, and the middle bit is affected along this axis, right. So by using this logic, what will be the representation here? Is it obvious? 0 right. This will be 1 1 0, this will be 1 0 1, and this will be 1 1 1, right. So what do you see? That the 2 sequences which formed your code words, you can think of these as your code words, right. Corresponding to an emission of 0, you are transmitting this word. This can be thought of as a code word. Similarly, 1 1 1 is a code word, right. These lie on diagonally opposite vertices, right. That's one way of looking at it.
So it will be diagonally opposite part.
Isn't it obvious? One vertex is here, the other is here. Do I need to explain that? I hope not. Okay. The other way of looking at it is, which are the received words which will be decoded as 0 0 0? This one, and this one, right. They correspond to a single error occurring for transmission of 0 0 0. If this is transmitted and a single error occurs, where will you land? Either here or here. That is one of the neighboring vertices which are at a what is called a unit Hamming distance. Hamming distance is the number of places in which two digital words differ, right? So we say the distance between them is unity. Distance between these two is also unity. Distance between these two is also unity. So these are this distance is called Hamming distance. Hamming was a gentleman who was well known in both logic theory as well as information theory. Also some codes by his name, Hamming codes. All right. Similarly, if you transmit 111, the words that will be possibly received after errors or single errors will be these, again neighboring vertices, right? And the reason why we could do single error correction was because all neighboring vertices with single errors, all vertices with single errors are at a distance of 1 from the actual vertex, from the true vertex, true code vertex, right? Whereas if you take a distance 2, for example, what is the distance between 111 and 010? It's 2, because you have to go like that or this, right? There are two bits which are different.
So what is this cube representing? So like,
I'm coming to that. Have you understood what I have said so far?
that is okay. Nearest neighbors, but like.
So be a bit patient. I'm coming to something from here. I mean, if you have not understood the picture itself, I can answer that question related to that. But what's the motivation for this picture is precisely where I'm coming to, right? Okay. Another way of looking at it is that if I draw two what I call Hamming spheres, you can think of this as some kind of an abstract space. It is not real space in which this cube is existing, because the only points which are really of interest to us are these points. These intermediate points which are drawn by lines don't really exist in this space, right? Because there is no way I can really get to one of these points. If I have what is called a Hamming space in which along each axis I can only take two values 0 and 1, right? Essentially I have a I call this a Hamming cube, and it's consisting of these 8 vertices, full stop. This Hamming cube is essentially a collection of these 8 vertices. Now I can therefore think of the role of redundancy in this way. It is precisely because of two reasons that I can do this error correction. One, that neighboring vertices were not used as code words. If you picked up one vertex as a code word, then you left out these neighboring vertices unassigned. They were not assigned as code words. Clear? Similarly, we picked up this as a code word. These neighboring vertices were not assigned as code words. Okay? Number 2, second point is that if I draw a sphere of radius unity around each of these points, around this point and on this point, they will be non-overlapping spheres. Now these are not again Euclidean spheres. What is a sphere? It is the locus of points at a unit distance from a center. In the Hamming space, therefore the sphere is essentially a collection of those points which are at a unit distance from this center. Which are these points? This point, and this point constitutes the Hamming sphere around this center. This point, and this point constitute Hamming sphere around this center, and they don't overlap. In the sense they don't have a common point. These two sets don't have a common point. So the second way of looking at it is that Hamming spheres of unit radius around each of the code words do not overlap. Right? It is these two reasons which help us achieve this error correction. Now if you were doing that 5 repetition code, you will now be working with a Hamming cube in 5 dimensions, not 3 dimensions. And in that 5-dimensional space, Hamming spheres of radius 2 around each of the 2 code words would be non-overlapping. Right? We will start from this picture next time to justify Shannon's result. Thank you.